So I want to, my goal with this talk is to introduce from very basic principles the notions of U-duality group and U-duality in four-dimensional supergravity, and demystify a bit what's behind these ideas. So this is going to be about U-duality in 4D Sugra. And by 4D Sugra, I mean here always the universal bosonic sector of 4D supergravity. So what are U-dualities in four-dimensional supergravity? U-dualities are, this is just an intuitive idea of what's behind these symmetries. These are accidental symmetries or extraordinary symmetries that exist because of the specific form of the theory. So this is a type of symmetry that a priori should not exist, or generically should not exist. But for the precise supergravity theories that appear because of supersymmetry, that are constrained because of supersymmetry, such accidental or extraordinary symmetries, depending on your point of view, do exist, right? So in order to introduce U-duality, the basic, most simple thing that one can do is to study the local Lagrangian. So this is what I'm going to do first. I'm going to study the local Lagrangian and introduce U-duality as a group of global symmetries of the local equations of motion. And then I will try to, time permitting, I will try to give a prescription of how this notion of U-duality generalizes to global supergravity, so to the global mathematical formulation of four-dimensional supergravity. So I will do it like... So, okay, local 4D supergravity. So we fix some open sets, contractible and orientable, U and V, and S is just some number. So these are just open sets, contractible and orientable. And we fix another number, MV, positive number, or 0. And, well, the configuration space of the local supergravity defined on U and V is just the set of triples G, phi, A, where G is a Lorentzian metric on U, phi is a smooth map from U to V, and A is a one form with values in R to the MV. So this is just the configuration space of the theory. And we can define this theory locally through the Lagrangian, which is a map from here to the four forms on U, and this Lagrangian is given explicitly as follows. So we evaluate it in a configuration, and this is minus a scalar curvature. This is the Einstein-Hilbert term, which we always have in this type of theories. And I will explain now what this is. This is like this. Okay, so this is everything. So what is this? Here we have chosen these symbols, and these are maps. This is a map from V to the square matrices NS times NS, real, and R and I are again maps to square matrices MV times MV with real entries. And we require that this is actually symmetric and positive definite. So it's a metric on V, and these ones are also symmetric, and only I is positive definite. And then this symbol here, G of I, is just the composition of these two maps. Okay, so this is the Lagrangian. It has the standard Einstein-Hilbert term. It has a nonlinear sigma model type of term for the components phi I of this map, and it has a type of gauge sector here, which involves the field strength of these one forms A. So here we have defined F lambda A. This is the A lambda, and this goes from 1 to MV. Come again? Yes, this is the Einstein-Hilbert term. This is a nonlinear sigma model type of term. And this is a novelty in this context, in the context of supergravity, which is a gauge sector coupled to scalars. So this defines locally a four-dimensional supergravity for every choice of data here, R, I, and G. So we conclude that for the Sugra is completely determined by a choice of GRI. This is the data that defines the local Lagrangian. This is the data that defines four-dimensional supergravity locally. Since both of these guys are symmetric maps, and maps into symmetric matrices, and I is positive definite, we can repackage this guy equivalently into a map, which we call the period matrix map, from V into the Siegel upper space of rank NV. Okay, so therefore, equivalently, for the Sugra theory is completely determined by a pair G, calligraphic G, calligraphic N. And we call these pairs electromagnetic structures. Regarding the calligraphic N and regarding the G, scalar structures. So these are scalar electromagnetic structures because they determine both the scalar sector and the gauge sector, which is a generalization of Maxwell theory, abelian Maxwell theory. Okay, so, well, since once you have the Lagrangian, you can obtain all equations of motion. You have, of course, the Einstein equations. the scalar equations, which come from variations of the scalars, and what people call usually the Maxwell equations, which correspond to the equations for the one forms A, which are locally interpreted as gauge fields. So we only need to worry at this point about the Maxwell equations. So the Maxwell equations. And the goal now is going to be to reinterpret geometrically the Maxwell equations in such a way that the existence of these accidental or extraordinary symmetries that we call U-dualities is apparent, okay? So, well, if you do the variational principle, you will get that the Maxwell equations are as follows. This is one way in which they can be presented. Okay. Where here I'm using matrix notation. Okay, so this is a matrix acting on a vector of two forms. This is a matrix acting on a vector of two forms. And, well, this is for variables G, phi, A, okay? And, well, we can rewrite this equation. This is equivalent to the following equation, which is written now in differential form. Minus equals 0. And again, for triples, G phi I. Okay, this is just the equation. So, sorry, here we need a H2. So clearly, if, for example, this map is 0, let me just say this is 0, and this is the identity, then these equations reduce to the standard Maxwell equations for A, okay? So let me just erase that real quick. Rather, here I meant the constant map, sorry, rather the identity, of course. It's a lot of water. Okay. So now, I'm gonna do a series of steps which are quite simple, but important to reinterpret everything appropriately. So now, since U is contractible, we can equivalently rewrite this equation simply as df equals 0 and this expression now. Now for triples, G phi F, where F is a vector valued 2, 4. Okay, this is equivalent. It's equivalent to the previous formulation clearly, and we can use it. We can use this new slight rewriting, local rewriting, to define now a following map. So we define the set of such triples by conf C, and we introduce, given a period matrix map, a map from the configuration space into the two forms valued now. So these are two forms in U, valued now in R to the 2mv. So these were two forms valued in R to the mv. These will be functions, sorry, these would be two forms values in R to the 2mv, and this goes from G P F into F, and here we use this equation. R phi F minus I phi dual of F. This is the map, right? And now what this map tells us is that we can simply write the Maxwell equations of four-dimensional supergravity as this map, the exterior derivative of this map applied to a configuration element equals to 0. So we can write them simply as this two form valued on U, valued in R to the 2mv, being closed. But of course, if we want to rewrite the equations of Maxwell in this way, we have to guarantee that this vector value 2 form can be written in this way, which is not always the case. This is what makes these equations non-trivial. This is not just a closeness condition for 2 forms valued in R to the 2mv. So therefore, we need to get a better insight on what is so special about the 2 forms valued in R to the 2mv that are of this form. And this is our first lemma, which says the following. So a vector value 2 form can be written as in here. So this is in the image of this map for a certain period matrix map and configuration if and only if it satisfies the following equation, which is algebraic in V minus J P calligraphic V, where this J is a map from V into the general linear group of R to the 2mv, given explicitly as follows. Given by, and this, just to get all the signs right, I need to check. Yes, this is minus I minus 1 R, I minus 1 minus. So this is just a combination that at this moment is, it just appears in this result. So it says that as the existence of a splitting in this way of a vector value 2 form on U for some period matrix map and configuration element is equivalent to this algebraic equation for the vector value 2 form in terms of some mysterious matrix valued map J, which is written in this form, where this calligraphic N is R plus II. So in terms of the period matrix map that we begin with. In particular, note that J square is Manus identity, okay? So this is a good step towards understanding when we have a splitting in this form, and this helps us rewriting the Maxwell equations. We can say now that the Maxwell equations, again, can be written simply as the closeness condition on two forms valued in R to the 2nb, such that these two forms are required to satisfy this condition. J of I V. Okay? But we haven't interpreted properly this matrix expression here, which is a bit unjustified at this moment. It just appears in the result. So this is my goal now. So for this, we have the following lemma again. Yeah. So lemma. So a matrix valued map from V to a general linear group can be written as here. So let me just name this like this. So can be written as in that expression for a period matrix map if and only if J restricted to P is a taming of the standard symplectic structure which I call omega S on R to the 2n V for every P in V. So what this means is that, well, omega S JP, this preserves omega, and this combination is positive definite on non-zero elements. So suddenly, starting just from the Maxwell equations of four-dimensional and gauge supergravity, we arrive to a condition that implies a symplectic structure on, in this case, vector space, which is necessarily of even dimension, given by the number of abelian gauge fields that we have in our theory. And using now this reinterpretation, so it turns out by this lemma that this funny-looking metric just corresponds to the geometric condition of this map
being a taming for the standard symplectic structure for every point. So we can rewrite the Maxwell equations. I will do it here. Simply in this form. So Maxwell equations. So the closeness condition for two forms with values in R to the 2mb such that well, this condition is satisfied. And this is for triples G, E, F, V, sorry. So actually, this type of rewriting can be done for all equations. We will not worry here about the other equations, but you can promote this theory, which was initially written in terms of G phi A, as a theory for variables G phi calligraphic V for all equations. And furthermore, this is well known from the literature we have, that there is a one-to-one correspondence. Let me lift this. It's a one-to-one correspondence between period matrix maps and Taming maps. So therefore, by these remarks that I'm doing, we can promote the configuration space of the four-dimensional supergravity determined by calligraphic G and calligraphic N as follows, or by, so this is the configuration space determined by this data, but this, we said, is equivalent to choosing or there is an equivalent choice of taming by this correspondence. So we can speak now about J. Instead of calligraphic G and calligraphic N, to determine the data that fixes completely the local Lagrangian of the theory as in here, we can choose to work with taming maps, because for such taming, we have a unique period matrix map that we can use to determine the theory. So then we can promote the configuration space of four-dimensional supergravity to triples of this form, where G is a Lorentzian metric again in U, P is a map, and now the novelty is that this calligraphic V is a two-form valued in R to the 2mv, such that this equation holds. For the taming map that we have chosen here. So suddenly, starting with a Lorentzian theory, we have arrived to a construction that involves a symplectic structure on a vector space whose dimension is prescribed by the number of gauge fields in the theory. So sometimes in the four-dimensional supergravity literature, people talk about the symplectic structure of supergravity. So this is one way of seeing how this symplectic structure appears, actually. So it comes out of the structure of the Maxwell equations. When you want to rewrite it in a terms that in our context is geometrically interpretable, as we will see now. So now we have rewritten the configuration, or reinterpreted we have, reconsider the configuration space of the theory in this way. And now what we are going to do, we are going to act with a group that is seemingly going to be out of the blue. Why do we act with this group? But you will see that it's justified. So the basic observation here is that if I have a solution, I will denote the set of solutions like this. It's a subset of the configuration space. Okay? So if I have a solution, G phi calligraphic V in Sol, then T applied to V is, of course, also closed for every T in GL R to the 2MB. Okay? But this needs to be elaborated further if we want to have such type of transformations in the solution space of our theory. So for this, which is a trivial observation, we consider, so given, let's say, given a 4D supergravity determined by calligraphic J and calligraphic G and calligraphic J on UV, then consider the group diffeomorphisms of V times the symplectic group, which is determined as the automorphism group of R to the 2MV with the standard symplectic structure that we mentioned before. So the point is that this diffeomorphism group of V, the target space of the nonlinear sigma model of the supergravity theory, times the symplectic group acts naturally on this set of Lorentzian metrics in U times maps times two forms, values in R to the 2MV. And note that for every pair G, J, the configuration and solution spaces of the corresponding supergravity belong to this space, right? So the action of this group in this space, we denote it by A, and it's very natural, given an element F E, this acts on G phi calligraphic V simply as follows. It does nothing to the metric. It composes F with phi, and then T acts linearly on V as a vector of two forms. So this is the action that we want to consider, right? So the basic question is the following. Does this action preserve the configuration space of a given supergravity? And the answer to this question is that in general, this action A does not preserve the configuration space of any supergravity. But instead, we have the following results. So let me erase here. And this is the basic idea or result which is behind why U-duality is so important in supergravity. So okay. So as I was saying, the question here is the following. What happens if we restrict for any given f this action to the configuration space of some supergravity theory? And the theorem is the following. Now, this action A restricted to the solution space, and similarly to the configuration space, but the main result is for the solution space of a supergravity defined or determined by G and J. This defines a bijection between the solution space of this theory and the solution space of this theory. Where, well, this is the push forward of the metric G in the target space V, and we have defined this combination. So therefore, the diffeomorphisms times, so what do we learn from this result? The result is that this action that we have introduced here as a natural action of the diffeomorphism group and the symplectic group in this set here, which contains every configuration space in supergravity, the result here is that this action restricted to a solution space defines a bijection with respect to the solution space of a different theory. So we learned that A defines a bijection between solutions and, well, configurations and solutions of different theories, of different supergravities. These are different supergravities in the sense that here the supergravity is defined by this pair, which are the couplings of the theory, and here this supergravity is determined by this other modified pair, and therefore has different couplings. And this transformation can be very complicated. So it can invert couplings. So therefore, it's a drastic change in the theory, or it can be a drastic change in the theory. And, well, if you have an identification between all configurations and solutions of different theories with different couplings, you may call this a duality. At least in the local classical sense that we are considering here. So, but then, since we have characterized precisely the supergravities that are related by this bijection, from this result, we can obtain the conditions that F and T need to satisfy in order to actually preserve the solution space of the corresponding supergravity. And this is the basis behind the definition of U-duality. So let me erase here. I'm running out of time. Quickly. Okay. So, well, I will use this first, actually. So now we can wonder about the following condition. Can we consider elements Ft in the diffeomorphisms times the symplectic group such that we obtain actually a map from the solutions to the given theory to the solutions of the same theory? This is the condition that we want to impose. And clearly, this will happen. This happens if these conditions are satisfied. This post forward satisfies this, and this equation is satisfied. So this just follows from this theorem here. And when this happens, when this type of transformation defined by this action actually preserves the solution space, then we say that that's a U-duality. So when this happens, then we say that this transformation here from the solution space Gj to solutions Gj is a U-duality. The term U-duality, this comes from string theory and the interpretation of such transformations in string theory, and well, we will not get into that. So now we can consider the group of all U-dualities. And the group of, let me erase that. Another group of all U-dualities, but now comes from the standard composition rule in this product group that we began with. And we have the following. So given a supergravity determined as usually by G and J, the U-duality group is by definition, from this condition and this theorem, the set of elements F, T in the diffeomorphism group of the target space V and the symplectic group such that this equation is satisfied. Therefore, this has to be an isometry. So we can write this here. Isometry of the given metric in V. And then we need to impose only this condition. So this condition simply says that Tj T minus 1 is equal to J composed with F. So what this is saying then is that if we consider the action by elements of the form, these pairs that satisfy this condition, then we preserve solution in configuration space. And what this is saying is that the composition with an isometry needs to be compensated by this action of a constant matrix. So in general, one should expect that there is no solution to this equation because you are trying to compensate a composition with a diffeomorphism via the action of a constant matrix which is the same at every point, right? The point is that for the type of J's that actually appear in supergravity, this equation has non-trivial solutions, and actually this U-duality group can be very complicated. That is why I was talking about accidental or extraordinary symmetries in the beginning of the talk, because a priori, this type of construction should give rise to no solution, actually. So to no extra symmetry. But for supergravity theories, this is not the case, and you can have very large U-duality groups. So let me give you just real quick an example. So I don't have time to go in detail in these examples, but nevertheless, where so, well, from this characterization, this local characterization of the U-duality group, you can obtain a couple of short exact sequences that you can use to characterize these U-duality groups. I don't have time now to discuss that, unfortunately, but, well, let me just mention directly a couple of examples. So, well, if we take a supergravity theory defined by calligraphic G calligraphic N such that this N calligraphic N is a constant map, then one can see that the U-duality group in this case is just isomorphic to the isometry group of the metric times the unitary group of rank MV. This is just simple situation. Slightly more complicated is the following example, in which take NV equals 1, V equals the upper half plane, and we take calligraphic N to be the identity map. So this is going to be a map from now H to H, and we can just take it to be the identity map. So in this case, one can also compute the U-duality group, and one gets that it fits into a short exact sequence of this type. And it is actually equal to SL2R. Now we have here a non-trivial, non-abelian Lie group. And let me give you just a slightly more complicated example in which we take NV equals 2, V again equals the upper half plane, and well, then our period matrix map is a map from H into SH2. This is Siegel upper space rank 2. And we take N evaluated at tau. Tau is an element in here to be this expression, which is actually the type of period matrix map that you get in the axiodilaton model of four-dimensional supergravity. Then it can be seen that the U-duality group fits into a short exact sequence of this type. Okay, where this is a Klein subgroup of order 4 of O2 embedded appropriately. So I don't have time to go into these details now, but what I want to transmit is that these groups can be quite non-trivial. They can be disconnected. They are not a direct product. Even they are a subgroup of a direct product. They may not be a direct product. And they correspond to these accidental or extraordinary symmetries that exist precisely for the type of Lagrangians that appear in four-dimensional supergravity. Okay, so now I don't have much time left, but let me give you a few remarks about what happens globally. So this was a geometric explanation of U-duality in local four-dimensional supergravity from first principles, as I said, starting with the Lagrangian, manipulating the Maxwell equations into something that is geometrically understandable. Suddenly there is a symplectic structure and some symplectic geometry around. We have a natural action of a direct product infinite dimensional group on configuration spaces, which relates configurations and solution spaces of different supergravities. And then we impose a condition to preserve the solution space of a given theory. And that's how we get, in this geometric context, to the notion of U-duality in supergravity. But this was only a local study. So the question is, what happens for the general formulation of these theories on manifolds of general topology? So for this, we need to consider the formulation, global formulation of 4D supergravity, which Kalin explained yesterday. So this is based, so in the same sense that here we need to fix UV and this local electromagnetic structure to fix uniquely a local Lagrangian that determines a given local supergravity. In this case, we need to fix a polarized Siegel bundle ETJ of type T over a scalar bundle pi h calligraphic h calligraphic g. So recall that this is a principal bundle with a structure group G equals the group of affine automorphisms of an integral symplectic torus that I denote simply by this, where this is the quotient by a symplectic lattice, canonical, quote-unquote, symplectic lattice of type T. And this can be identified simply with a explicit model, which is R B over lambda T, semi-direct product with the automorphism group of this lattice, which is a modified Siegel group. Okay, so it's a principal bundle whose structure group, the connected component of the identity, is a torus, but it has a very complicated group of components, infinite and non-compact. So this is the bundle whose connections describe locally the type of gauge fields that appear here in this local formulation of the theory. So the main question that one answers with this global formulation on this polarized Siegel bundle is the following. How we describe gauge fields, abelian gauge fields, in supergravity mathematically. This is the main question that this formulation addresses. So locally, we have a bunch of abelian gauge fields, which are a bunch of one forms. But the main question here is, okay, but how do we describe this thing mathematically speaking? So the answer is that this is a connection on a principal bundle, which is a polarized Siegel bundle. And then this pi is a submersion over our four-dimensional base manifold M, equipped with an Ehresmann connection. Again? So surjective submersion in this. A connection H and a vertical metric, vertical Riemannian metric. And since I don't have much time, I just want to transmit the idea of what happens with this U-duality in this context. So now in this context, let me erase this. Examples. So in this context, we have to identify the configuration space. And then we need to propose what's the analog of the U-duality group for this global formulation. So, as I was saying, for the supergravity, now this is the general formulation of the bosonic sector, is completely determined by this data, the scalar bundle pi h g, and the polarized Siegel bundle of type T. Okay, and what's the configuration space? So the configuration space of the theory determined by this data, J, is just the set of triples again, A, such that G is now a Lorentzian metric in M. S is a section of pi, and A is a connection on the pullback of P by S. So this is the configuration space. And as you say, the isomorphism type of P may depend on the configuration chosen, of which A, what I mean is the isomorphism type of the principal bundle of which A is a connection may depend on the configuration chosen. So let me change. So I will finish real quick, but so this is the configuration space, and in this context, we also have the Einstein scalar and Maxwell equations, and the Maxwell equations are rewritten or are given in this geometric formulation as a polarized self-duality condition for the curvature of this connection. So, yeah, FA is automatically closed, indeed. Yeah. So, but what I wanted to say to end the talk is that there is an analog of the U-duality group. Locally, we were considering this group to begin with the analysis of the symmetries. So this group is now promoted in this setup to the automorphisms of our Siegel bundle that cover the automorphisms of the submersion that preserve the base point. So in the following sense, these are automorphisms of our Siegel bundle, and therefore they cover diffeomorphisms of the basis, but the basis is the total space of this vibration. Okay, so we impose the following condition such that the diffeomorphism that it covers satisfies this. And locally, what this gives you is precisely this type of group. So there is a global notion of this duality group, or some people call this the pseudo-duality group, in terms of automorphisms of a principal bundle whose connections, once pullbacked, are the gauge fields of the theory, with the requirement that they cover a special type of diffeomorphisms. And then, just to truly end, we have a similar theorem in which we define the natural action of this group on this configuration space, on the configuration space or solution space of a given theory, and we obtain a bijection between the solution space of the given supergravity determined by all this data and the solution space of another supergravity whose defining data is obtained from the data that defines the original supergravity by the natural action of the automorphism. And we obtain a complete analogous picture of what happens in 4 dimensions, but globally, for every Siegel bundle on a submersion on a scalar bundle, which locally restricts to the formulation that I just given. And well, unfortunately, I'm running out of time, so I will stop here. Thanks.